topic of my presentation today will be on process integration and design optimization. During the design process, engineers often have to go through a decision-making process which requires them to optimize the operations of the system by adjusting hundreds or even thousands of parameters which affect the system's response. The big challenge for this is the amount of calculations which involve hundreds or thousands of design parameters without having a good idea how long the computation will take, or if it is even necessary to investigate some certain parameters. An advanced tool would possess the functionalities that allows an engineer to highlight the most influential parameters and focus on those having the highest sensitivity on the objectives. So this allows us to reduce the design space and simplify the optimization task. So what is an optimization process? Optimization in general is a process of finding is a process of minimizing or maximizing an objective using a search techniques under some certain constraints. So the diagram here shows a general design process, starting with a model with the initial design or the initial parameter set. You simulate to see how the system behaves. Often the system doesn't satisfy with the first try, so you will need to try another set of parameters. The process is then repeated until you find the optimal design by satisfying an objective function under some constraint conditions. So let's first talk about the tools that we're going to be using for the model development and optimizations. The first tools that we're going to be talking about is MapleSim. So MapleSim is a physical modeling and simulation tools developed for modeling and simulating physical systems. You can think about an electrical network, automotive systems, hydraulic pumps, etc. They can all be modeled in MapleSim. So how can MapleSim help with the optimization process? Under the hood is Maple, a powerful math engine that allows us to the user to tackle complex problems using its programming and analysis capabilities. Maple also possesses two optimization toolboxes, the local and the global optimization toolboxes. And the highlight of which is the global optimization toolbox, which helps find the best solutions in the presence of multiple local optima. Let's use the following example to learn how Maple and MapleSim helps as a modeling and analysis tools. So what you see on the screen right now is a model diagram of a skip lifting system in MapleSim. This is part of a giant mining system called a dual truck mobile sizer made by a German company called F.L. Smith. This skip lifting system takes the material from the mining trucks, these are huge mining trucks, and they dump the materials into the conveyor belt system, which then be transported to a processing plant. The system is lifted by two hydraulic cylinders controlled using a complex hydraulic systems. The geometrical parameters, as you can see on the screen here, x1, y1, z1, and x2, y2, z2 through x5, y5, and z5 have a huge influence on the behaviors of the systems. The hydraulic pressures, the vertical forces, and the vibration when the skip touches the ground. So it is desirable to find out how the system responds to every change of the key the geometrical parameters. This picture shows more details of the hydraulic circuits that control the system. So the hydraulic circuit is assisted by a hydraulic accumulator, which can be seen on the left corner of the screen. The seamless integration between Maple and MapleSim allows the user to tackle this problem easily. Not only the user can run the simulation in MapleSim environment and observe the response of the system to the parameter changes, but also he can implement his own algorithm, including parameter sweeping and global optimization searches to find optimal design. This is a worksheet programmed in Maple, which allows you to specify and vary the design parameters of interest. Then do parameter sweep on these parameters and plot the hydraulic pressure of the skip cylinders. So here we can see that the vertical position on the first column, you can see that the vertical position of the skip system is fixed at 9.143. And by changing the lateral position x1 between 7 and 9 meters, we can see how the hydraulic pressure changes in the plot below. And we can see the same kind of behavior when we keep the parameter x1 stationary, and then by changing the parameter y1 between 8 and 10, we can also see the plot for the hydraulic pressure in the graph below as well. For multi-object optimization problems and optimization processes that requires integration of multiple simulation or computation platforms, we are going to use Optimus. So Optimus is an optimization and process integration software system developed by our sister company, Noesis. There are multiple ways user can define an optimization process using MapleSim and Optimus. For example, the user can generate optimized C code, which can can then be read by Optimus easily. The user can also implement the Modelica for the MapleSim model, which can then be run in Optimus as well. And the easiest way is to use a Maple connector plugin, which allows the user to read a Maple worksheet or MapleSim model and then simulate that in Optimus environment, and apply a variety of optimizations, DOE processes for the MapleSim model. We are going to use the following example of a series hybrid electric vehicle system to demonstrate the use of Optimus for optimization of a MapleSim model. This is a complete model of a series hybrid electric vehicle developed in MapleSim. From right to left, we see that we have a vehicle chassis and the tires, which allows the vehicle to roll on the roll on the highway. And the front axle of the vehicle is connected to an electric motor through an induction gearbox. The power to drive the wheel was drawn from a battery pack through a power control unit, which takes input from the driver through the speed controller. A series HEV model also has an internal combustion engine which provides the power to drive the wheel and to recharge the battery pack. And there's also a cooling system to help reduce the temperature on the battery and the internal combustion engine as well. So the design parameters are defined and grouped into separate parameter boxes. By changing these parameters, we can observe the system response by looking at the plots defined through the probes, as can be seen in the model diagram. So once we have our high fidelity system model, we can move on to the optimization task. For this exercise, we are targeting the following optimizations. We want to minimize the fuel consumption. We want to minimize the engine power loss, maximize the engine torques, so that's to have the more powerful the powertrain. We also want to keep the temperature of the battery pack to be below 315 Kelvin, and we also try to keep the battery current below a threshold that can so that it does not harm the battery life. So the column on the right hand side shows the constraints for each objective functions that we need to optimize. The challenge now is to determine how to achieve these 5 objectives simultaneously. Which system parameters influence the values of these objectives, and how should they be set in order for that all of the 5 objectives are met? So how do we go about selecting the influential parameters? The approach that we took was to use the design of experiments. The purpose of the exercise is to maximize the gain of information while keeping the numbers of evaluations to a minimum. Through engineering experience, an initial set of 13 parameters were identified for further investigations. These were then subjected to a latent hypercube sampling, where a set of 50 experiments were computed, covering a complete design range for each variable. But even with this identified 13 parameters, we need to distill the option further to determine a smaller groups that we really need to focus on for optimization. To do this, we need to calculate the linear correlation factor for each parameter, which is how much of a direct effect the value of that parameter has on the system. So this can be positive or a negative effect. For example, if an increase in the value of a parameter causes an increase in the response of the system, then it has a positive linear correlation factor, and vice versa. So using engineering experience, a set of 13 initial parameters were selected, and by applying statistical modeling, tests were designed to determine which of them has the greatest influence on the system. By looking at the correlation matrix, a set of 7 parameters are identified as having the greatest influence. So these 7 parameters are the minimum state of charge thresholds, the number of cells in the battery pack, the engine bore in meter, the strokes of the engine also in meter, the specific surface area of the battery positive electrodes, the nominal voltage of the electric motor, and the nominal voltage and also the nominal voltage of the electric motors. In this design, we have 5 objectives that need to be fulfilled simultaneously. Statistically modeling has identified 7 parameters that have the greatest influence on the systems, but there are multiple combinations for the values of the 7 parameters that enables all the 5 objectives to be met simultaneously. So as an illustration, here are a few possible combinations of the 7 parameters. In each case, all the 5 design objectives are met to a varying degree. For example, for combination 2, the fuel consumption is great. We are aiming for about 2 and 8 liters per 100 kilometers. Now, the battery temperature is strictly within that range, should be less than 315 K, but it only just scrapes into that range. So the question is, how many possible permutations of parameter values are there? And more importantly, which one of those is the optimum setting for the system? These questions are answered through a multi-objective optimization. In this case, we used the Pareto line method applied by the Optimus software platform. The tool calculates and plots all the points, which are called the Pareto points, at which all our design objectives are met simultaneously, each to some extent. So now some of those points will represent an optimum solution for one particular objective, but the majority of the points will be true compromise points, where all the objectives are met to some degree, without any one necessarily faring better than the others. So given all of these plot points, the question is, which one point representing a specific combination of parameters should be selected as the solution for the hybrid electric vehicle system? The way to determine this is to examine the sensitivity in each Pareto point. Let's cast our mind back to the table on the previous slides. For the second combination of parameters, we see that the fuel consumption is great, but the battery temperature only just comes within the acceptable range. So what happens if there is an ever so slight change in any one of the parameter values, that could easily push the temperature way over 315 degrees, and then that the objective is no longer met. So we're looking to find the point with the most robust performance, which are the points that is robust to small design changes, so that if small perturbations of the design parameters happen, the performance of the system doesn't decrease below the design quality levels. So using the Optimus platform, we calculated the sigma values for each point, which show how much the response is affected, and found the point with the smallest sigma values that happens to be the point that was optimized for power loss. So as a result, we have a compromise point plus of power loss, number 5, which was selected as the HV solutions. So this this compromise point guarantees the best solution for power loss, in addition to meeting all the other objectives. So this table shows a comparison of the results from the initial design and the optimum design, which shows the relative and absolute improvements of the objective functions. So to summarize my presentation today, we have seen that system level modeling enables us to manage the design of a complex vehicle model in an easy and intuitive way. And by using high fidelity models, we are able to develop a complex system such as escape lifting systems, or even a complete system of a hybrid electric vehicle model that not only captures the electrical mechanical behaviors, but also accounted for the physical characteristics of a real systems, while ensuring that we are able to meet the model true to life vehicle behavior. And using statistical analysis, we are able to determine which parameters have the greatest influence on the output of the system, given that there were multiple design goals to be met. An optimum set of parameters could not be determined that simultaneously satisfied all the design goals, and rather the complete set of the compromise solution has to be determined and analyzed. And because the model was fully characterized, we were able to perform sensitivity studies for each of the compromise solutions and applied advanced optimization to determine the optimum combination of parameters. Through system level modeling, we were able to meet the design goals and achieve the most optimum design significantly faster, safer, and more cost efficient than those building and testing multiple physical prototypes. And that concludes my presentation today. Thank you for the attention. If you have any question for me, I would be happy to answer.